All right, hello there. So let's work on this review sheet here. So number 1 says, given the graph of the function 1 over x plus 4 plus 1, name the following. So what are the transformations to arrive at this function from the graph of 1 over x? So remember, 1 over x is like your basic rational function, and it gets graphed right here and right here. The asymptotes, you have a vertical asymptote at x equals 0. You have a horizontal asymptote at y equals 0. So these items right here change those around. So the x plus 4 makes you move to the left 4. So this moves your function to the left 4. And the plus 1 makes you move up 1, just like with all of your other functions this year. When something is with the x, a number added or subtracted, you move left to right. And when something is afterwards, it's up or down. The domain. So you can see in this problem right here, the domain, anytime you have a rational function, you have to worry about what's happening in the denominator. So right here, the denominator cannot be 0, so that means that x cannot be 4. So my domain is all real numbers where x cannot be negative 4. All right, what's the vertical asymptote? So the domain and the vertical asymptote in this case are basically the same thing. You can see it graphed right here as well. X equals negative 4. Remember, the vertical asymptote is a line that you're not going to cross. The horizontal asymptote, that comes from, it's moving up. Basically, you're moving this up 1. So that is y equals 1. But it also comes from when you put this problem together. Because you might look at that and be like, oh, well, it's 1 over x plus 4. The horizontal asymptote is 0. But that's not true, because when you put this together, you have 1 over x plus 4, plus if I give the 1 a common denominator of x plus 4, and then x plus 4, because that's x plus 4 of x plus 4 is 1. So this becomes 1 plus x plus 4, so that would be x plus 5 over x plus 4. And then you start to see that, oh, well, the numerator and the denominator have matching exponents, have matching degrees, and so you take the leading coefficient, and since the leading coefficient in both cases is 1, then that's why it's y equals 1. All right, so down below here, the domain, x cannot be 2, because that would cause the denominator to go to 0 right there. The equation of the vertical asymptote is the same thing. X equals 2 is your vertical asymptote. The horizontal asymptote. So for the horizontal asymptote, remember, we're going to compare. We're going to look at the x's on the top and the bottom, and the numerator and the denominator. Well, the x's, they match. They have a matching degree. So I'm going to take the leading coefficients, 3 over 1. Because there's a 3 in front of the x on top, and there's a 1 in front of the x on the bottom. So 3 over 1 is 3. So y equals 3. So I'm going to go ahead and graph those on the picture. So x equals 2. Y equals 3. And that basically kind of frames up your graph. All right, the x-intercept and the y-intercept. Now the x-intercept is when the y value equals 0. So that means that you want the y value, or the function itself, to equal 0. So when does a function equal 0? It's when the numerator equals 0. So 3x plus 5 has to equal 0. So if you solve that, take away 5, divide by 3, you get negative 5/3. So negative 5/3, 0. So negative 5/3, that's like 1 2/3. So negative 1 2/3 is about right here. All right, and then the y-intercept is when x is 0. So that's really easy to do, because all you're going to do is basically plug 0 in for these x's right here. And so when you do that, you get 0 plus 5 on top, and you get 0 minus 2 on bottom. So you end up with positive 5 over negative 2, or negative 5 halves, right? And so that's 2.5. So 0 and negative 2.5 would be about right here. Okay. Now the end behavior, you're going to see it on the picture in a minute, but the end behavior matches your horizontal asymptote. So it's going to be 3 in both cases, because I know what's going to happen here. All right, so let's go to Desmos and see. 3x plus 5 over x minus 2. right, and so you can zoom in or what have you, but look there, you can see an intercept right there, 0, -2.5. You can see -5/3 and 0. And then you can also see the rest of your graph. And so we're going to sketch it based on that. If you want to, you can also graph your asymptotes to confirm those. All right, so I'm going to graph it up to the right. We don't have to be super perfect. Down here, I'm going to make sure I go through these 2 points, and I'm going to graph the rest of it. Okay, and you can see that what's going on here is that your end behavior, as x goes to infinity, your graph goes towards 3. As x goes to -infinity, your graph goes up towards 3. And so the end behavior is 3, in fact. All right, so down here, just practice of doing some domain and vertical asymptotes and horizontal asymptotes and plugging in numbers. All right, so I'm going to leave this one in the middle till last because it's going to take a little bit of work, but let's look at my domain. So in this problem right here, x cannot be 3. So all real numbers, x cannot be 3, because the bottom 3 minus 3 would make 0. The vertical asymptote is the same thing, x equals 3. Horizontal asymptote, when I look at my numerator and my denominator, they have matching x's. So I'm going to take the 2 over the 1, so y equals 2. And this function down here, I'm going to plug in 4. So it means I'm going to plug in 4 for this x and for this x right here. So in the numerator, I get 2 times 4, so I get 8 plus 1 is 9. So I get 9 over. And the bottom, I get 4 minus 3. 4 minus 3 is 1. So 9 over 1 is 9. All right. Looking at the next problem on the right. Actually, we'll just go ahead and do the second one as well right now. So that one I'm going to take, and notice there's some factoring going on that needs to be done. I got 5x squared over, I get 2 plus x and 2 minus x. So my domain is this, all real numbers, x cannot be, now that cannot be 2 or -2, so plus or minus 2, because that would cause either parentheses there to go to 0. 2 plus -2 is 0, and 2 minus 2 is 0, so I can't use those numbers. These are also my vertical asymptotes. All right, my horizontal asymptote, I look back to my original. My original problem, when I look at it, has x squared and x squared. So that means I take the leading coefficients. Well, the leading coefficient on the numerator is 5, and the denominator has a leading coefficient of -1, even though it's the second thing. It's not really, it's out of order. So 5 over -1 means you have -5 for your leading coefficient. All right, and then the bottom down here says plug in -2. Well, wait a minute, that's one of the numbers that I'm not allowed to plug in. So this is not possible. This is undefined. All right, on the last problem, my domain, all real numbers where you cannot use -5. That's my vertical asymptote as well. And my horizontal asymptote. In this case, the numerator has no x, and the denominator has an x. So the numerator has a smaller degree than the denominator. So it means I'm automatically going to say my horizontal asymptote is 0. All right, so when I plug in 0, I plug 0 in for x right here, and I'm going to have 3 over 5. That's my answer. All right, let's see. So on this page, this beginning part right here, we're back to some oldie but goodies here. So we're going to have to factor everything and reduce. So I'm going to factor 4x squared minus 9 into 2x plus 3 and 2x minus 3. In the denominator, I have 2x and x. I have to make a 3. So I think I'm going to put 3 here and 1 there. Let's check that out. That's 3x, and this is 2x, and I want to get a 5x. So if I make them both positive, that'll work. All right. And look, I can already see a cancellation. All right. Over on the right side, I can take a 2 out of here, so 2, which leaves me x plus 2. And the denominator, I'm going to start off with a 2x and x. Excuse me. And I have to make a 6, so I think I'll try 3 and 2 again. So 3 here and 2 there. This is 4x, and this is 3x. So that can make a 1 in the middle, positive 4 minus 3. So plus here and minus there. I was doing that because I noticed these 2x's and 3's there, so I was trying to make something that would cancel and see if that would work as a clue. All right, so there's my work, and I'm going to do some canceling. 2x minus 3, 2x plus 3, oh, x plus 2's. All right, so there's my answer, 2 over x plus 1. All right, remember this type of problem here. This is a complex fraction. So remember, you're going to keep r minus 6 in the numerator over 24 r to the 7th. You're going to flip up the bottom. So, because dividing is like multiplying by the reciprocal. So 8r to the 3rd over 6 minus r. Remember that these are opposites of each other, so you can cancel them out, but you have to put a negative 1 in their place. So really what I have right now is negative 8r to the 3rd over 24r to the 7th. So it might help you notice that 8 and 24 reduce to a 1 and a 3. And r3 and r7, this cancels out, and this has 4 left because you subtract your exponents. All right, so we have negative 1 basically over 3r to the 4th. That's my answer. All right, number 6, I'm subtracting these expressions. So when you add or subtract, you need a common denominator. So in this case, I think it's probably obvious to you. You need x minus 3 and x plus 7 as your common denominator. And so 4x is going to receive an x plus 7, minus 5 is going to receive an x minus 3, and then you have to work that out. So if I do that, I get 4x squared plus 28x minus 5x plus 15. So if I clean that up, I got 4x squared plus 23x plus 15. All right, all over x minus 3 and x plus 7. And you are done. And every once in a while you might want to, sometimes if you don't see that answer, or sometimes you have to check and see, make sure this doesn't factor, but this one doesn't, and so you're finished. But every once in a while, you know, something cancels, but in this case it doesn't. All right, so number 7, when you're solving this equation, if you actually solve this equation out, this one right here, this guy, you solve that, these are the answers that you end up getting, x equals 2 and x equals negative 6. But it turns out that you cannot accept both answers. The only answer that you're allowed to accept is negative 6. So the reason for that is because of right here and right here. Remember, 2 is one of the excluded values that you would never accept. It's going to be an extraneous solution. And so that's what we're talking about here. So the domain of this problem is all real numbers where x is not allowed to be 0, nor is it allowed to be positive 2. So since you have mentioned that in your domain, that is why x equals 6, negative 6 is the only answer. Because getting an answer of 2 is an extraneous solution, and you don't want that. So y is the final solution to this simply x equals negative 6 is because 2 is not in the domain of the problem, because we make the bottom equal to 0. All right, and number 8, the easiest way to think of this problem is to just cross multiply here. So I get, let's see, 2x times x minus 1 equals 3 times 3x plus 2. And if I go down here, my domain or my excluded values, x cannot be 1. And also right here, x cannot be negative 2/3 if you set that equal to 0. All right, so let's solve this out. I got 2x squared minus 2x equals 9x plus 6. So I'm going to bring everything over to the left side. So I got 2x squared minus 11x, and that 6 is just going to pop over, minus 6 equals 0. All right, so let's factor and let's see what we get. So 2x and x, I don't know, how about 6 and 1? Because look right there, I'll get 12x, and here I'll get my 1x, so that way I can do negative 12 plus 1 to make my negative 11. Okay, so my answers are 6 and negative 1/2. And neither of those break the rules of my domain and my excluded values, so that's it. All right, on number 9. First thing to notice on number 9 is that x squared minus 9 is really x plus 3 and x minus 3. So it's just a combination of the other two. All right, so we're going to multiply through by our common denominator, or basically going to try and make everything have a common denominator. So the 5x plus 1 already has x plus 3 and x minus 3. But the 9, to make this match to x plus 3 and x minus 3, the 9 would need to receive an x minus 3. And then the 1 would have to receive an x plus 3 to make it have the same denominator. So we're using this method of figuring out the common denominator because what we're going to do here is when we have an equation and everything already has a common denominator, what I can do is I can just steal the numerators and solve that equation. The denominators already match, so who needs them? All I'm going to do is steal the numerators. So I got 5x plus 1 equals 9 times x minus 3 plus 1 times x plus 3, which is what you're used to seeing, and I was just trying to explain it out the long way, but we did that at the beginning, but we haven't done it for a while maybe. All right, so let's see, 5x plus 1. Over here I have 9x minus 27 plus x plus 3. So notice there's no x squared, so this is going to be an easy problem to solve. 5x plus 1, this is going to be 10x minus 24. I'm going to take it down here. I'm going to take away 5x from both sides, so I'm going to have 1 equals 5x minus 24. And then I'm going to add 24 to the left. So I got 5x equals, 24, I was thinking ahead, 25. So my answer is x equals 5. Now let's go back to those excluded values. Remember, x can never be whatever makes the denominator 0, and so that would be plus or minus 3. But the answer I got was x equals 5, so that's perfectly fine. And that is it.